Hello, dear students. Today I'm going to discuss question number 5 and question number 6 of the chapter on fluid mechanics. So, the question number 5 says the viscosity of a gas decreases with increase in temperature, increases with increase in temperature, is independent of temperature, is independent of pressure for very high pressure intensities. So, this question discusses viscosity of a gas and its relationship with temperature and pressure. So let us have a look. If we observe a gas and we plot its viscosity and temperature, as we go on increasing the temperature of a gas, the viscosity increases. And if we observe a liquid, against the rising temperature, its viscosity decreases. The viscosity is the resistance to deformation. So if we try to deform a liquid, the resistance which a liquid would offer to this deformation is viscosity. Similarly, if there is a gas and we try to deform this gas, it would resist this deformation, and this resistance to deformation is termed as viscosity. Now, in this question, we need to observe the relationship between temperature and the viscosity. As we go on increasing the temperature in a gas, the molecules in the gas start colliding with each other. The randomness increases. So if we try to deform this gas with the rising temperature, its resistance to this deformation would only increase. But in a liquid, a reverse behavior is observed. If we deform a liquid, if we try to move this container carrying the liquid, and we go on increasing the temperature as well, the resistance to this deformation would decrease with the rising temperature. So this is the behavior of viscosity in a gas and in a liquid with the rising temperature. you increase the temperature of a gas, the viscosity or the resistance to deformation or the resistance to the movement would increase. But in liquid, as you go on increasing the temperature, the liquid will start flowing with ease. This enables us to answer this question. The viscosity of a gas decreases with increase in temperature, which is wrong, which is basically the property of a liquid in which the viscosity or the resistance to deformation decreases with the increase in temperature. So the first option is true for a liquid. And the second option, which says the viscosity of a gas increases with the increase in temperature. The third option says the viscosity of a gas is independent of temperature, which is not true because the viscosity is a temperature dependent property both for a liquid and a gas. Now the fourth option says the viscosity of a gas is independent of pressure for very high pressure intensities. Let us observe the fourth option. If we go on increasing the pressure and we transition from the low pressure to a high pressure intensity, at low pressures, the viscosity would remain unchanged in a gas. If the pressure is low, it won't affect the movement in this gas. But if the intensity of pressure is increased, if we increase this pressure intensity, it would have an impact on the movement of these gas molecules. So if we plot viscosity and pressure at high pressure intensities, suppose this is a zone of high pressure and this is a zone of low pressure. At high pressure intensities, the viscosity would increase. You increase the pressure, you have more resistance to movement in the gas molecules. But at fairly low pressure intensities, the viscosity would be constant. It won't have any impact on the viscosity of a gas. So the option D, which says that the viscosity of a gas is independent of pressure for very high pressure conditions, is wrong. At high pressure intensities, the viscosity of a gas would increase. So the correct option for the question number 5 would be B, which says the viscosity of a gas increases with the temperature. Increase the temperature, you get more resistance to the movement in gas. So that answers our fifth question. Now let us discuss the question number 6. Question number 6 says Newton's law of viscosity. So before exploring the options of this question, let us have a look at the Newton's law of viscosity. Newton's law of viscosity says tau equals mu times du upon dy, where tau is shear stress in a fluid, mu is dynamic viscosity, and dou by dou y, u is velocity and y is the distance between two layers in a fluid. So dou by dou y is the velocity gradient. Let us consider a fluid flowing between these two boundaries. This is a boundary. This is a boundary. It can be a pipe, or we can consider a fluid moving over a single boundary. This can be a fluid moving in a canal, right? So let us consider this fluid flowing between these two boundaries. This is a flowing fluid. If the fluid is a real fluid, which practically all fluids are, if it's a real fluid, then close to the boundary, this fluid, even though it's flowing between these two boundaries, the fluid in contact with the boundary would be in a state of rest. That is, the velocity of the fluid close to the boundary would be 0. Similarly, on this boundary, the velocity of the fluid would be 0. If I plot the velocity profile of this fluid moving between these two boundaries, it would look something like this. At the boundary, the fluid would be in a state of rest, so the velocity is 0. And as I go on moving away from the boundary, the velocity of the fluid would increase. And then on the another boundary, it would again be in a state of rest. So typically, this is how the velocity profile of a fluid flowing between two boundaries would look like. So If we observe these velocities, say u1, u2, u3, and so on, there is a velocity gradient. That is, as we cover more distance from the pipe boundary, the velocity of the fluid layers is different. So there is a velocity gradient. Now, to explore this gradient a little bit further, let us consider a small element in this flowing fluid. Let us zoom in on this element here. Let us take 2 points in this fluid element. Point 1, this is the point 1, and point 2, this is the point 2. Suppose this point has a velocity of u1, say this is moving at u1, and this is moving slightly at a higher velocity than the point 1, so its velocity is u2. So this point u1 and this point is flowing with u2. So u2 minus u1 would be the relative velocity of point 2 with respect to point 1. And this differential velocity can be written as du. So taking this point as a point of reference, the point 2 is moving with the velocity of du. And if I observe point 2 for an infinitesimally small time duration dt, it would cover some distance. At the starting of my time duration, it would be here, and say at the end of my time duration dt, it would have moved here. And in this time duration, it would cover a distance ds. All right. If we take the distance between these 2 points as dy, so this fluid element, which was like this at the beginning of this time duration dt, now it has transitioned to a new shape like this. All right. So if I explore this triangle, which has been formed as a result of the fluid movement, this is the distance ds, which the point 2 has covered in an infinitesimally small time duration dt, and dy is the small distance between these 2 layers, layer 1 in the fluid and layer 2 in the fluid. And as a result of this flow, for an infinitesimally small time duration dt, this fluid element, which was in the shape of a square or a rectangle earlier, has deformed to a new shape. If I measure this deformation in terms of this angle, which was 0 at the start of this time duration dt, and now it is d theta. That is, this layer in the fluid connecting the points 1, 2 has transitioned over a small angle d theta, and now this boundary is something like this. If I take the tangent of this small angle, tan of this angle, the small deformation, would be the opposite side upon the adjacent side in this triangle. Since this deformation is really small, because it is the deformation of an infinitesimally small element which we have observed in this fluid flow, we can take this tangent equal to the deformation itself, and that would be ds upon dy, where this ds is the small distance covered by point 2 moving with the relative velocity of du and for a time duration of dt. Since distance is the product of velocity and time. So if we rearrange this equation a little bit, ds would be du times dt upon dy. Therefore, on rearranging this equation, we get d theta upon dt is du upon dy. So the result is here. This is the rate of deformation or the rate of change of this angle equals the velocity gradient, that is du over dy. So this velocity gradient in Newton's law of viscosity is basically the rate of change of deformation or the rate of change of strain, which is equal to the velocity gradient. So we can rewrite Newton's law of viscosity as tau equals mu times du upon dy, or tau equals mu times d theta upon dt. That is, the rate of shear, that is, the shear stress equals the dynamic viscosity or the coefficient of dynamic viscosity times the velocity gradient, or the shear stress equals the coefficient of viscosity times the rate of change of strain or rate of strain deformation or the rate of deformation in this fluid. Therefore, Newton's law of viscosity relates shear stress with the rate of deformation or the velocity gradient. So, at a given temperature and pressure, that is, if these two parameters are kept constant, the shear stress upon the rate of deformation is constant, and that constant is the coefficient of viscosity. So this is what the Newton's law of viscosity talks about. That is, at a given temperature and pressure, the shear stress between any two layers in a fluid, in a moving fluid, equals the coefficient of viscosity times the rate of deformation or the velocity gradient. Because the velocity gradient is equal to the rate of change of strain or the rate of deformation which we have observed here. Now let us explore the options in this question. Newton's law of viscosity relates intensity of pressure and rate of angular deformation. Yes, the Newton's law of viscosity talks about the rate of angular deformation, but it doesn't deal with the intensity of pressure. Though angular deformation is a parameter in the Newton's law of viscosity, but the intensity of pressure is not. So, option first is ruled out. Let us take a look at the second option, which says that the Newton's law of viscosity relates shear stress and rate of angular deformation. Yes, this option looks probable. But let us have a look at the option C. Newton's law of viscosity relates shear stress, viscosity, and temperature. The Newton's law of viscosity talks about shear stress in a fluid, viscosity of a fluid, but it does not talk about temperature. Then the option D is Newton's law of viscosity relates viscosity and rate of angular deformation. The Newton's law of viscosity has viscosity, has the rate of angular deformation, but does it relate them? Does it relate these two parameters? Let us have a look. The Newton's law of viscosity relates shear stress and the rate of deformation, because we have learned that at a given temperature and pressure, the ratio of the shear stress and the rate of angular deformation is constant, and that constant is mu, which is dynamic viscosity or the viscosity. So, having a look at the options again, the option B looks most probable, because this is what Newton's law of viscosity is all about. It relates shear stress and the rate of angular deformation. Yes, it does have viscosity in it as a parameter. It does have the rate of angular deformation, but the relationship in the Newton's law of viscosity is between the shear stress and the rate of angular deformation, whose ratio at a given temperature and pressure is constant, and that constant is viscosity. So the answer of our question number 6 is B. That is, the Newton's law of viscosity relates shear stress and the rate of angular deformation. Thank you for watching.